right, hello everyone. We're looking at lesson 25 on polarity. So with this one, it's really just going to build on the last one with shapes. Understanding the different shapes and getting them right is going to be very important here. So what happens whenever you have a diatomic molecule bond, for example, like two hydrogens or two chlorines, you have no polarity. So if you have hydrogen with hydrogen, they're fighting over your two electrons. They're both equal strength, so neither one of them wins. So electrons stay right in the middle. So you have a negative region in the center, a positive region where each hydrogen is because they have a bunch of protons. And so you have a negative in the middle, positive on the outside. There's no difference on either side, so there's no polarity. So it's non-polar. So what will happen, though, when you do something like this, you have partial charges. So let's do okay. Let me do this. So let me take a step back. So that's like if you have hydrogen, there's not a full positive charge, It's like these partial charges right there, but it's non-polar. So if you look at it, if you look at the molecule, you won't see either side as a positive or negative. Now, let's replace that with chlorine. If you look at the periodic table, remember, the simplified version is that atoms in the upper right of the periodic table hog all the electrons. So what's going to happen, sure, hydrogen and chlorine are sharing two electrons, but those two electrons, chlorine's going to hog. So like if you're sharing something with a friend, but they're hogging it all, like sure, you're technically sharing it, but it's more theirs than yours. So what that's going to do is make this side negative and this side positive. But because they're sharing, it's not like full custody was given over to the chlorine. They're sharing. So what that means it's going to do, you're going to have the higher electronegativity closer to chlorine, and so we're going to have a partial charge on each side. And we call this a polar covalent bond. So what we're going to do, since they don't have full charges, we use this little Greek symbol, the lowercase delta, or the delta symbol. And so we'll just say, we'll go like this. We'll say it's a partial charge of positive and it's a partial charge of negative. So you're saying it's slightly positive over here, slightly negative over there. And so what we do to say that the whole molecule has polarity, the whole molecule is polar, is we take an arrow, instead of drawing these little deltas with the little weird squiggly thing, we're just going to make one big arrow where the tail has a plus sign telling you where the positive side is, and then the arrow tells you where the negative side is. It's almost like it's telling you where the electrons go. So what we would do for this molecule, yeah, we understand it's partially positive there, partially positive, tongue twister. Partially positive here, partially negative over here. So we'll go like this. You take the positive, you take the negative, and just draw an arrow that goes through like this. And so we're saying, look, this is the partially positive side, that's partially negative side. Polarity goes in that direction. Okay? So you're going to do this thing. Instead of drawing a bunch of positive negatives, you just draw this arrow with a plus on the tip, telling you which direction the charges would go. So if that's the case, you would expect all molecules with a polar bond to be a polar molecule. So you would say, well, if this thing has a polar bond, it has to be a polar molecule, right? So it's like if one bond is polar, isn't the whole thing going to be polar? That's not always the case. Let me show you what I mean. This is why it's so important in the last lesson to do the shapes, so you can kind of picture where everything's going to be. So let's take CH4. I know that CH4 is tetrahedral. It'll technically have that 3D shape where you have like a tripod on bottom and one pointing up. For the sake of this, we're going to do it in 2 dimensions. I'll be okay us drawing it like a cross. So if you have carbon with 4 electrons, when carbon bonds with hydrogen, who's going to win in the tug of war of electrons? Just so you know, hydrogen almost always loses. So this will have its own little polarity going towards carbon. And you might think, okay, this is going to be a polar molecule. It has to be. Well, let's finish it. It's CH4 we're talking about. So here's another H. And so what's going to happen here? Polarity goes towards carbon. Here's another H. Polarity goes towards carbon. Here's another H. Polarity goes towards carbon. This is why it's important to understand the shapes. You'll see as we do this how this plays out. So what would happen if you're in the middle and you have 4 different friends tie a rope to you, and they all go in 4 different corners, and they're all equally strong, and they all pull? Are you going to go in any direction? No. It's probably going to be uncomfortable because you get squeezed. But if you're getting pulled in 4 different, and if you're getting pulled up and down by the same amount, left and right by the same amount, they'll cancel each other out. You won't go anywhere. So it's like this polarity cancels out that. This cancels out that. In case you're thinking, what about the 3D version of this? If we did this in 3D, it would be, it's this kind of thing where this is going towards us, this is going towards us, this is going away from us. So it's this tripod and straight up. What happens is these tripods, their front and back and left and right directions cancel out, and all that's left is a combined upward force, which would be canceled out by this single bond's downward force. So even in 3D, it works out where they all end up going towards the center and cancel each other out. So that's why I'm okay with you drawing it like this to simplify it, because this behaves the same way as the 3D will. So let's just go with this. You're end up going to having no polarity. It's going to be nonpolar. And why is that? Because these all cancel each other out. Okay, so it's nonpolar. So this is how you can have a polar bond in a molecule, and overall the whole thing is nonpolar. Let's do CO2. So, and this is where it's extremely important to know the shapes, if this is going to be linear or bent. So carbon is going to look like this. How do I know it's a linear and not a bent? Because carbon has no extra electrons. So when carbon and oxygen fight for electrons, they might both go towards oxygen, but it's like a tug of war, and it cancels out, so it's nonpolar. Once again, nonpolar. Okay, and then let's do H2O. Now this is an example. You might have looked at CO2 and said, hey, CO2 is nonpolar. Maybe H2O should also be nonpolar. This is why shapes are so important. O is going to have 6 electrons. It has extra electrons on there. And remember what we did last lesson? That's going to make it bent. Remember, this is why you're not supposed to spread it out and make it linear. You make it bent. So who wins between H and O? O wins. O wins. Do those cancel each other out? If they were on opposite sides, they would, but it's bent. So I want you to imagine if you take an object and you're pushing it in this direction, but you're also pushing it up at the same time, what's going to happen? It's going to go diagonal, both directions at the same time. So the final polarity of this will be that right there. So the final answer, and this doesn't have to be, you could have drawn it over here, you could have drawn it over here, but the final answer is going to be polarity going up or left. To clarify something too, if you draw this slightly different, where you draw it like this, I'm okay with that. Then you would have a different answer though, because now you're going to have your polarity go like that. So it's not that the answer is up or left. The answer is the combined direction of the 2 hydrogens. So when you do these, you're going to have to submit drawings today. Make sure that I understand there's a multitude of correct answers depending on how you draw that. All right, let's do COS. That'll be my last example. I'll let you work on these, and then I will make sure to post a video where I go over the problems that you have. So COS. So carbon, oxygen, and sulfur is going to look like this. So, okay, so carbon loses to oxygen. That's no problem. Carbon loses to sulfur. That's no problem. Okay, but now we have a situation. Yeah, there's a tug of war, but we don't have the same molecule. We don't have 2 O's or 2 S's. So can we expect them to cancel out? Probably not. So, it's like if you have somebody really weak in the middle and you have somebody on each side pulling on them, that's not going to work. So so what I want you to do is you're going to look at your periodic table, which you might see a reflection. I'm pulling it up on my computer. I have a setting where I can't switch between tabs. That's why I can't pull it up for you to look at. So what you're going to do, you're going to go to classwork. You're going to pull up your periodic table, and you're going to look at the competition now is between oxygen and sulfur. Because yeah, it's obvious. Carbon loses to oxygen, it loses to sulfur. But now it's oxygen and sulfur fighting to pull the electrons to either side. So who wins? If you look at the periodic table, oxygen is number 8, sulfur is below it, number 16. And remember, it's in general, the upper right corner is what wins. So oxygen is up higher than sulfur, so we can assume that would mean that this is going to go to oxygen. And that'll be our final polarity. Now, I'm not going to use the word polarity in these. When I go over the answers, I'm going to use this word right here, dipole moment. Because the magnitude and direction of the molecular polarity, so all of it put together, creates what we call the dipole moment. So when you do these, you'll have your final dipole moment, which will be this, which is part of the answers for these. So this puts so many skills together. You need to make a Lewis structure, which is from weeks ago. You need to then take the Lewis structure and get the shape right, which was VSEPR we did last lesson. And then you're going to need to use the electronegativity from months ago and figure out which one wins the tug of war of electrons. This is the kind of thing I was saying where chemistry, no single lesson is impossible, but it builds and it builds. So make sure that you try this today. There will be a video below with all of the correct answers. And if you have any questions, please feel free to ask.